Okay, so the last topic in lecture 12, which is continuing our discussion of loops, is to do with recursion. Okay, so we are just going to, this is pretty much the only place that recursion will be mentioned in this course. You might find that there's a question about it in the tutorial and maybe one or two in the test. So it may get a few mentions here and there in Complex 101 and other places, but it's not a major topic. So if you go on and do more computer science, you get to use recursion quite a bit. So recursion is another way of doing iteration. So we've looked at for loops, while loops, do while loops so far. This is a completely different way of creating a loop, and the basic way of doing it, a way of doing loops using recursion, is to make the program reference itself. So the idea is that the program runs and then it references a version of itself. So it runs a version of itself, which in turn runs a version of itself, which in turn runs a version of itself, and so on. And that this is another way of getting a type of iteration. Here's a bit of a joke down here. So the dictionary definition of recursion is see recursion. So recursion is defined in terms of itself. Let's have another look at what we might mean. So we've got a pseudocode for an algorithm here called climbing the stairs. And if we read through that, we can see it's a fairly simple algorithm. It has just one if statement. So the if statement says if you're not at the top of the stairs, then go up one step. Okay, that makes sense. So the loop body's here, so go up one step, then use algorithm to climb the stairs, right? So run the same algorithm again. So if you're not at the top of the steps, go up one step, then use algorithm to climb the stairs. So the algorithm starts again. If you're not at the top of the stairs, go up one step, then use algorithm to climb the stairs, and so on. So if you run this algorithm, it's going to keep on invoking versions of itself until this if state, the clause of the if statement, the expression is false. When this is false, we do the else part, which simply says stop, you've reached the top. Okay, so if you're not at the top of the stairs is false, then it must be true that you're at the top of the stairs, so you stop. Okay, so the idea here is the algorithm, all the algorithm knows how to do is go up one step. That's the only work it does. But it can reach the top of an entire staircase by continuously invoking itself over and over again until you reach the top. Here's a nice illustration. So we're starting at the bottom at point A. So if you're not at the top of the stairs, go up one step, then use the algorithm climb to the top of the stairs. So now we're at B. Again, if you're not at the top of the stairs, go up one step, then use the algorithm to climb stairs. There we go again. If you're not at the top of the stairs, go up one step, then use the algorithm. We're still not at the top, so run it again, go up one step, and at this point we're at the top of the stairs, so the else clause kicks in and we stop. Okay, so that's a pretty contrived and simplistic example. And in fact, it's not a very good example of recursion because you could have just used one of the loops that we have already looked at. So we could have used a while loop, and got some while pseudocode here. So while we're not at the top of the stairs, that's the clause, the expression for the while loop. So while we're not at the top of the stairs, go up one step. Okay, this will become false when we reach the top, so it does the same thing. Or we could use a for loop. If we know how many steps there are, we can just say for n equals 1, so starting at the bottom step, while n is less than or equal to the number of steps, so while we're not at the top, increase n by 1 on each iteration of the loop, and the body of the loop will be go up one step. Okay, so we didn't really need to use recursion to solve this problem. We could have just used the normal loop, one of the ones we've been looking at so far. So what is a problem where recursion makes sense? Well, it turns out that there are a lot of problems where recursion makes sense. There are a lot of problems where you can't simply apply a while loop or a for loop or a do while loop and come up with a program that's simple and solves the problem. So recursion can sometimes solve problems that aren't very easily solved using other methods of iteration. Let's look at a classic example of this. One of these, the classic example where you need to use recursion is called the Towers of Hanoi. And this is a problem that's been around for many hundreds, even thousands of years. The problem is to take this set of disks and get them from peg A to peg C in the same order. So we've got a large disk at the bottom, and then a smaller disk, and then a smaller disk, and so on to the very smallest disk at the top. Okay, so we want to shift the whole pile from this peg to this peg, but there's one constraint. The constraint is that you can't put a larger peg on top of a smaller peg. So we couldn't have, say, 4, 5, 3, 2, 1, and then 5 on top of that. That would be illegal. So we can never place a disk on another one that's smaller than itself. We do, however, have this intermediate peg here, which can be used to as a storage place for disks as we move everything across to peg C. Okay, so let's have a go at trying to solve this problem. So in fact, I've got a solution here which illustrates the way to solve this problem for 3 pegs. So we start off here. We've got just 3 pegs, small, medium and large. We want to shift them to from peg A to peg C. So how do we do that? Well, first of all, we take the small peg across. Okay, so this is the situation here. We've got the small peg here, and then we move 2 pegs from here to here. Okay. Well, actually, we've got one. Yeah, remove 1 peg. Sorry, from this peg to this peg. So we end up with the green peg here, which is the situation there. Then we shift the red peg onto here. Okay, and then we get to this situation here where we've got 2 pegs in the middle, and we've got this large one here, but we can freely move that one since there's nothing on top of it. So we move that peg across, and now by this point we've got 1 peg in its final position. So we've got 1 peg across where it's supposed to go. Then we move the red peg onto this one here, freeing up the green peg. So that's this situation here. And the green peg can then go onto the blue peg, which is where it's meant to go, and then the red peg goes on top of the green peg. And we end up with all 3 pegs moved across to their correct position. Okay? So we've solved the problem for 3 pegs. Now let's just have a little think about how this solution works. Okay, so if you'll notice the sequence of states, you'll notice that often we need to shift 2 pegs at a time. Okay, so in order to move this blue peg at the bottom, we've got to move both of these 2 out of the way first. So in the initial state, which is this one here, we want this peg, this blue disc, moved to here, but we can't do that till we've moved 2 of these out of the way. So one of the steps, and we can think of one of the steps in solving this problem as moving 2 pegs at a time. And the 2 pegs at a time, it consists of several steps. So if we look at these steps 1, 2, 3, 4, by the time we get to state 4, what we've got is 2 pegs moved to the center. Okay, so they start. We can think of this whole sequence here as one command to move 2 pegs to this peg. Alright, so we can free up this one. Okay, that's the idea. So we've got these 2 pegs through these 4 steps. We can effectively think of these as one step of moving 2 pegs to the center. right? And then we do this single step, which is moving the blue peg here. Okay. Now, when we get to this point, we're in another similar situation where we have to move 2 pegs again. Okay, so we need to move 2 pegs from here onto here. Okay, and again, we've got 4 steps to do that. So the 4 steps are like moving individual pegs, but the end result here is that these 2 pegs from here have been shifted onto this large blue peg. All right, so what we're saying is we can take the problem of moving 3 pegs from one, well, 3 discs from one peg to another. We can take that larger, more complicated problem and solve it by breaking it down into the problem of moving 2 pegs. Okay, we need to do that a couple of times. We move the 2 top pegs to the center peg first. Okay, then we move the big blue peg across to its correct position. Then we move the 2 center pegs again onto here. Okay, so moving 3 pegs is basically broken down into 3 instructions. Move the first 2 pegs, the top 2 discs, to the center peg. Move the big disc across to its final position, and then move the 2 center discs onto their final position. Okay, so we can break the 3 problem down into a program with that we can break the 3 disc problem down into a problem with 3 instructions involving only moving 2 discs. Okay, here's the some pseudocode for that again. So if we start here, to move 3 discs from peg A to peg C, we first move 2 discs from A to B. That's moving these 2 to here. Then we move the 3rd disc, that's the big blue one, across to here. Then we move 2 discs from peg B to peg C. So these 2 go to peg C. Right? This is the whole program for solving the 3 disc version of the Tales of Hanoi. However, in order to write the program that does this, we need to understand how to first move 2 discs from peg A to peg B. Okay, and so here's the program for moving 2 discs. So to move 2 discs from peg A to peg B, we first move 1 disc, okay, from peg A to C, then we move the 2nd disc to peg B, and then we move 1 disc from peg C to peg B. Okay. So this 2 disc problem is very similar to the 3 disc problem, except that instead of it involving 3 discs and 2 discs, we now involve 2 discs and 1 disc. The 1 disc problem itself is extremely simple. We just move a disc. Okay, we can just do that. We don't need to worry about trying to solve it in a whole bunch of steps. It's just 1 step. Okay, the 2 disc problem takes a total of 4 steps. And then the 3 disc problem takes a total of 8 steps. So we gradually, as the problem difficulty increases with more discs being added, we're gradually increasing the number of steps we need to take. And we can see here that there's another 2 disc problem. This is the 2nd one, which is moving 2 discs from peg B to peg C here. Okay. And we can generalize that. So we may be faced with an 8 disc problem. It turns out that we can take exactly the same approach. So in order to move 8 discs from one peg to another, we need to first move 7 discs onto the temporary peg. Then we move the 8th big disc, that'll be a very big one, onto its final destination. And then we move the 7 discs from the temporary peg onto the final destination peg. Okay, so if n is 8, then we can solve the 8 disc problem, but then we need to solve 2 7 disc problems. Okay, and so if we solve the 7 disc problem, we then can the 7 disc problem is basically this algorithm here with n equals 7. Okay, so we can basically change n to 7, and that means that we then need to, in order to solve the 7 disk problem, we need to solve the 6 disk problem. So twice. Okay, we need to solve it twice. In order to solve the 6 disk problem, we need to solve the 5 disk problem twice. In order to solve the 5 disk problem, we need to solve the 4 disk problem twice, and so on, and so on, and so on, until we get to the point where n is 2. Okay, in order to solve the 2 disk problem once, we need to solve the 1 disk problem twice, and the 1 disk problem is very simple. It's just moving the disk from one peg to another. And so we can expand the pseudocode there to include the case where n equals 1, which is simply moving a single disk from one peg to another.